Okay, Assalamualaikum warahmatullahi wabarakatuh. So we continue with Biobuilding 2, chapter number 3, the dynamics of Biobuilding 2. So we want to see how the molecule are moving in our body that moving in the water. Okay, so we want to see how it moves and how it reacts with the other molecule, and also how can it come from one point to another. Okay, so these are because of division. Okay, so these are from our AMM heat equation, or in this case is division equation. Del C over del T equal to d del squared C over dx squared, where C is the concentration. Okay, the concentration. So you can see that here. You can see that this compartment, or this part, has a more molecule, but when we take out this separator, so it will mix up. From this molecule can move to this part, and at the end it will have the same the average number of molecule in each part. Okay, so how fast the molecule move, we can find it, or we can see it from this diffusion coefficient, this one d. Okay, so this diffusion equation given by the Stokes-Einstein equation, where F is the frictional coefficient. Okay, so when this molecule move, so from our mechanics we know that when we move there is a friction. Okay, so this is our friction equation. So d equal to kBt over F. So kb is the Boltzmann constant, T is the temperature. Okay, so here if we assume that the molecule is in a spherical form, or macam bola. Okay, so the frictional coefficient for this shape is F equal to 6 pi eta times R. Okay, so where R is the radius of diffusion molecule in meter, and eta is the viscosity of the solvent. Okay, so the same molecule, if we put in the different solvent, we will have the different frictional coefficient. Okay, so if we put this into the previous equation, d kb over t over f equal to kbt over 6 pi eta r. Okay, so for the spherical form, so these are, we can calculate the diffusion constant or diffusion coefficient using this equation. Okay, we know the viscosity of the solvent, the radius of the molecule, the temperature, so we get this equation. Okay, so kalau kita ada bola rugby, the molecule is like a bola rugby, so we are going to have a different frictional coefficient. Okay, and if the molecule is like let's say aeroplane, so we are going to have a different formula for this frictional coefficient. Okay, so how can we find the diffusion constant? So what affect the diffusion constant? So here the diffusion constant depends on the nature of the molecule and the solvent. Okay, the viscosity of the solvent, the shape of the molecule, the weight of the molecule, the residue, or the R subunit, or R subunit of the molecule. Okay, so also the friction of the molecule. So it depend, diffusion constant depend on this uh, factor or parameter. Okay, so here we can see that the large molecule have a smaller diffusion constant. Okay, logik kan? the heavier molecule will move much slower. Okay. Okay, and the division constant also depend on the temperature, as we can see in this equation. So it depend on the temperature T. Okay, so here is the division constant for uh, some molecule or some molecule in the water at room temperature. This is considered room temperature is considered 25 degree Celsius. Okay, so you can see here 2 times 10, 9 to 6.9 times 10 to the power minus 12. Okay. Okay, and we also see that diffusion constant, or we can also say that diffusion constant can also be calculated using this equation, D equal to KBT over 6 pi eta 4 over T 3 M over rho pi and A. Okay, so these are the molecular weight of the molecule. These are the density of the molecule, and Na is the Avogadro number. Okay, so here we can see that if this M is high, or M is heavier, so this one, the diffusion constant will be much slower. Okay, or much slower. M increase, D decrease. Okay, so D for a wide range of molecular weight fall within a comparative small range. Okay, square root of 3. So, if the molecule diffuse, okay, so macam kita berjalan, okay, if we Brownian motion, so when we move around in the water or we move around the campus, at t equals 0, what is our coordinate? And at t equal to, let's say, 10 minutes, what are our uh, coordinate? Okay, so because of the Brownian motion, the motion moving randomly. Okay, so the the length of movement of the molecule can be calculated using this equation. The R, the length, R squared equals 6d times t. Okay. So these are d is the diffusion constant, t is the time. Okay, so we can estimate where is the molecule at time t. Okay, from the initial point. Okay, and diffusion is low in bulk liquid. Okay, so here we can see that in bulk liquid, because it need to take move around the liquid. Contohnya macam kita lah, kalau kalau dalam kesesakan ataupun dalam banyak orang, okay, so kalau kita nak pergi dari satu tempat ke satu tempat, akan bertembung, terpaksa tukar jalan sebelum sampai ke tempat yang dituju. But within the confined cell, it will be much faster. Okay, because kalau dalam let's say in the gas theory, okay, so when the gas meeting the other gas more frequently, then it will diffuse much faster because it gain momentum. Okay, so the division, so how can we find the division, or how can we get the division equation? So starting from this Fick's law, okay, using again the same picture as before. Okay, so the rate of division per unit area in a direction perpendicular to the area is proportional to the gradient of concentration of fluid in that direction. Okay, so I'm moving to, okay, so here J equal to minus D dc over dx. Okay, the flux. So berapa banyak, contohnya dalam sejam berapa banyak kereta melalui laluan tol, okay, ataupun pondok tol. Okay, so kalau waktu sibuk, banyak, waktu tak sibuk tak banyak. Okay, so the J is the flood of particle, number of particle passing through an imaginary normal surface of unit area per unit of time is related to the force that push them minus dc over dx. Okay, so if there is a force, then it will be much faster. Okay, and next is the osmosis. Okay, osmosis is the transport of molecule in the fluid through a semi-permeable membrane due an imbalance in its concentration on either side of the membrane. Okay, so here these are membrane. The molecule cannot pass through, but here we can see that here is a small number of molecule. Here we have a higher uh, density of molecule. So the water will permeate this membrane, flooding this site, and we can see that the concentration of this side and this side will be maybe the same. Okay, so these are the back pressure. So we have this value. Okay, so osmotic pressure of the solution containing n mole of solute per volume V of solvent is, and this is one half equation from our chemistry, P equal to NV over RT, N over V times RT. Okay, so we can get this pressure. Okay, so why osmosis is important? So these are the, we are going to see in the respiratory respiratory system. Okay, so how the oxygen exchange with the carbon dioxide. Okay, so osmosis between root and groundwater is thought to be responsible for the transfer of water into many plants. Okay, so groundwater is purer and hence has a high water concentration than sap. So osmosis move water into the root, then water in sap is then transferred by osmosis into cell, causing them to swell with increased pressure. Okay, so these are the osmosis. So how the molecule, or the, in this case, the molecule diffuse in the or the water diffuse across the membrane. Okay, or in this case the ion or the cation moving from one side to other side. Okay, so analysis of particle flow or the molecule flow across the membrane must consider the influence of pressure gradient. Okay, so uh, from the high pressure to the low pressure, the movement, Coulomb interaction. So let's say uh, A side is Na plus, and B side we have Cl minus. Okay, so we have the Coulomb interaction. Attraction. So let's say Na plus will move to the other side. Okay, and then also the concentration different. Okay, so here we have two types. Okay, again using the division equation. So division without source. Okay, so these are the example: ink in water. Okay, so we put the ink in the water and let the ink diffuse by itself to whole uh, uh, to the whole space of the container. Okay, so we just put at one spot, but after some time it will diffuse to all part of the container. Okay, and the next one is diffusion with source. So we have the ink, we put the ink in the beaker, and then we stir the water, so it will pour the ink to diffuse much faster. Okay, so here we have the source. Okay, the source. Okay, so these are the diffusion without the source. with initial value given by, so these are component A, A1, A2, and these are membrane. So here we see that concentration A, concentration 1 is greater than concentration 2. So the molecule from concentration 1 will move past the membrane if it's permeable, or it can pass the membrane to C2 and making the concentration in C1 equal to the concentration in C2. Okay, so taking the example from our AMM Nagel page 03. So using this equation or division equation and this initial value, so we are going to get this equation. Okay, or we can get this solution. Okay, so tau naught is equal to kinetic time for concentration equilibrium. So how fast it will component 1 become equal to component 2. Okay, or the concentration in compartment 1 become equal to concentration of compartment 2. So here C1, C2, 0 naught, C1, 0, C2, 0. So after some time, it will be after T infinity. So both compartments will have the same concentration. Okay, the division with a source. Okay, so the concentration of each side, internal and external, will be, so again using example number 3, page 04, Nagel 8 edition. Okay, so we are going to get using this the initial value, so we are going to get C internal and C external equal to this equation. Okay, or CA, CB. Kalau ini compartment A, this are compartment B. Okay, so we have this equation. Okay, so looking at this equation, putting it in R. Okay, so for the when Q greater than 0, so there will pressure, let's say the source in A. Okay, so it will speed up the concentration. Okay, so for this Q less than 0, okay, so the concentration or the external without a source, so the 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 concentration or the molecule from outside will enter the into the internal side. Okay, so these are the example. Okay, so contohnya macam pembuluh darah kita. Okay, pembuluh darah kita concentration dia, contohnya concentration dia lebih kecil daripada yang dekat organ kita. Okay, so maknanya daripada organ akan masuk ke salur darah kita. Contohnya macam carbon dioxide. Okay, dalam darah carbon dioxide kurang, tapi dalam organ carbon dioxide tinggi. So carbon dioxide akan pindah daripada organ ke pembuluh darah, tu darah, dan dibawa ke jantung dan dikeluarkan. Okay, so that is the example. Okay, so next is the vibration. Okay, so here these are vibration and affecting the conventional transition. Okay, so a molecule consisting of n atom has 3n nuclear degree of freedom. So this one is from your statistical physics, I believe. Okay, or from the material science or detail. Okay, so of the external degree of freedom regarding the translational and rotational motion of a whole molecule as a rigid body. Okay, translational, dia molecule moving. Rotational, sambil dia moving tu, sambil dia berjalan tu, dia berputar. Okay. The remaining 3 n minus 6 internal degree of freedom Each number of case molecule can be identified as covalent bond and dihedral angle of rotation above the bond. Okay, so this one is the vibration. Okay, ini molecule, this one molecule moving, this one molecule uh, rotate, and these are vibration between the bond. Okay, so here these are the example. So vibration of molecule. So you can C and M1, M2. So it will vibrate. So this one also it can vibrate. Okay, so these are vibration in this direction. Vibration, this see, these are stretching. These are stretching, and these are uh, apa, tekan. Okay, and this one is strain. Okay, so we can see here from our quantum mechanics, vibrational energy, E vibration for two molecule, and this one is for general, n plus 1 over 2 h bar of times omega. So omega is the natural angular velocity. Kappa over mu, where mu is reduced mass and kappa is the string constant of this one. Okay, the string constant. Okay, so from this vibration, so we are going to have a typical structure. Molecule has approximately 10 to the power 4 internal degree of freedom. Okay, so ini banyak. So you can see here, it can vibrate. So if the energy of vibration is greater than this point, this peak, so it can move to another conformation, okay, or configuration. Let's say these are cis, and then this one is can be trans. Okay, so it need to exceed this energy. Okay, so the vibration you can see here by 300K, localized vibration, stretching and bending yang kita tunjuk sini, uh, stretching and bending. Okay, and greater than this 300K, collective vibration, meaning torsional motion about the bond. Okay, so we have this torsional motion. Okay, so this one will do the vibration. Okay, so from this vibration or this vibration, so it can be changed into another shape. So we have this global conformation. Okay, so satu molekul boleh ada dalam berbanyak bentuk. Okay, so these are the example, number of atom and conformation. So kalau kita ada dua atom saja, so here we can see only this conformation. Kalau kita ada empat, okay, so ada this one. This is Fibonacci number or whatever number. Okay, so if we have 3, so you can see here we have 2 kosong, 2 1, 2. This is 2. This is 2 1, 2 2, 2 3. Okay, 2 3 8. Okay, so we have this confirmation. So here we can see that for m, 2 to the power of m, okay, or 10 to the power of m, global 100. So we obtain via this method the numerical number of 10 to the power 100, 10 to the power of 100 global conventional state. Okay, maknanya satu molekul tu boleh ada 10 to the power of 100 phase or shape. Okay, but only 1 or 2 conversion are exist. Walaupun kita ada kata 1 juta 2 juta confirmation, tapi that is active and inactive, we we only have 2 confirmation, A and B. So we can uh, model it as A or B. So native, so you can see native folded or non-native unorganized or unfolded state. Okay, so the last one. Okay, so this one is we want to see just see protein native state, time scale of conventional transition in the protein native state of via various experimental technique. Okay, so this NMR, chemokinetic numerical simulation, multiple spectroscopy, phase climb technique, hydrogen exchange. Okay, so we can get this value. Okay, so we can see here this is much better, uh, much better value or much better number. Okay, so this one. Okay, so thank you.